Hi guys, we're going to do a little gas stoichiometry today. It's really not that much different than regular stoichiometry, we just have to add in the part for the gas. If you recall, any stoichiometry problem the key is a mole to mole ratio. So we have that mole of A converting to mole of B, and we all know to do that we're going to use the mole ratios again. Now we can start with the mass, we could start with particles, we could go to mass, or we could go to particles. We know that if we're going to convert from mass to moles, that we're going to divide by the molar mass, and when we go from moles to mass, we're going to multiply by the molar mass. Same thing down here. If we're starting with particles, we're going to divide by Avogadro's number, and if we want to convert from moles to particles, we're going to multiply by Avogadro's number. Ooh, it's a bad NA, but that's an NA, guys. But what do we do if we start with a gas? If I have a gas, and it's going to be given to me as a volume, and we're going to be in liters, and then we would want to convert it to, I don't want to move that, we would want to convert it to moles of A or moles of B. But now this is where it gets tricky. We have to look at the conditions of which the gas is given to us. More specifically, we have to look at its temperature and pressure. At STP, 1 mole of any gas will occupy 22.4 liters of space. And that STP, again, is defined as 1 atmosphere and 0 degrees Celsius. If we're at STP, it makes it very simple because all I have to do is divide my volume, as I just move everything, divide by my volume by 22.4 liters to convert to moles. And if I'm at moles, I'm going to multiply my moles by 22.4 liters. Now remember, this only works for gases. A solid isn't going, if I have 1 mole of solid, it's not going to occupy 22.4 liters, and the same thing for a liquid. This is only for gases. Now, if I am not at STP conditions, meaning that my temperature is not 0 degrees Celsius and my pressure is not 1, I'm going to have to use PV equals nRT. Sodium azide is a compound used in the production of nitrogen gas in airbags. If we look at the equation below, it rapidly decomposes to produce nitrogen gas and solid sodium. The solid sodium is slightly problematic, but we're not going to worry about that right now. According to the equation, for every 2 moles of sodium azide I have, I can produce 3 moles of nitrogen, which is a gas, and 2 moles of sodium. The question asks how much sodium azide is needed to inflate the driver's airbag to 55 liters, which is approximately the standard size of an airbag, at STP. Now, bells should be going off in your head when we hear that it's at STP, because I know at STP, 1 mole occupies 22.4 liters, and this is going to make the stoichiometry fairly easy. So if we look real fast, we're at, I shouldn't have done that. Let's see if I can erase that. Oh, look at that. We are at 55 liters. It is at STP, and we want to solve for how much sodium azide. And whenever you see how much, that typically implies that we are dealing with grams. So I start with 55 liters of nitrogen being produced. Because I'm at STP, I know that for every mole of nitrogen, it's going to occupy 22.4 liters. Now that I have canceled my liters of N2, I'm at moles of nitrogen. I'm going to go to my balanced equation to see that for every 2 moles of sodium azide that I want to produce, that I need 3 moles of nitrogen. My moles of nitrogen have canceled. I'm now at moles of sodium azide. Molar mass of sodium azide, which is the mass of 1 sodium and 3 nitrogen, is 65.01 grams for every 1 mole. My moles of sodium azide cancel, and now by the power of the calculator, I see that I need approximately 106 grams of sodium azide to get my airbag to inflate. Now what happens if we're not at STP? If we're not at STP, we're going to have to use PV equals nRT. So let's look at the same problem, but this time we're going to change the conditions. Let's look at this problem where we're not at STP. So it reads, how much sodium azide is needed to inflate an airbag to 55 liters, let's change my colors, 55 liters at 31 degrees Celsius and 0.967 ATM. So because I'm not at STP, and I know that because it's not 0 degrees Celsius and 1 ATM, I'm going to have to use PV equals nRT. So our first step is going to have to be to solve for using PV equals nRT. So let's see what we got. In the problem that it tells me that my volume is 55 liters. Got an equal sign there. My pressure is 0.9 0.967 atm. My temperature is 31 degrees Celsius, and if I convert this to Kelvin, it's 304 Kelvin. Because my pressure is given in atms, R is going to equal 0.0821. This is a liter atmosphere mole Kelvin. And finally, I don't know my moles. To solve for my moles, we're going to use PV equals nRT, and we're going to solve for moles. And then once I have my moles, I can jump onto the train tracks to solve my stoichiometry problem to get me 2 grams of sodium azide. So from PV equals nRT, I know that this is going to equal PV divided by RT. So now I'm just going to plug everything in. My pressure is 0.967. It's harder to write on here than you thought. Volume is 55 liters. Divided by 0.0821 times 304. And this gives me that I'm going to have 2.131 moles of N2 is going to be needed to fill that 55 liters at 31 degrees Celsius and 0.967 atm. This gives me halfway through my problem. To finish it, I need to convert from my moles of sodium or my moles of nitrogen 2 grams of sodium azide. Don't worry about sig figs right now because we'll finish that later on. So now the stoichiometry starts. I need to slide everything up. Can't really slide up anymore, so we'll just do it down here. We've just calculated that at these conditions, we need to produce 2.131 moles of nitrogen to inflate that airbag to 55 degrees Celsius, or to 55 liters. To figure out the sodium azide required to produce that much nitrogen, if you remember from the equation above, for every 3 moles of nitrogen, we need 2 moles of sodium azide. Now my moles of nitrogen cancel. I need to cancel my moles of sodium azide, and I know that 1 mole of sodium azide is 65.01 grams per mole. My moles of sodium azide cancel, and by the power of the calculator, this is about 92.4 grams needed. As you can see, there is a difference between the amount of sodium azide needed if our conditions change from STP. Now just a quick recap, if we start at STP, if our conditions stay at STP, we can simply use this factor. We know that 1 mole occupies 22.4 liters at 0 degrees Celsius and 1 atm. However, if we're not at STP, to solve for either the volume of the gas or the moles of the gas, we'll have to use PV equals nRT.